So this is the last topic for this chapter, and once we do that, we're going to go back into JUMP and go through the process of using JUMP to do all the techniques that we have seen so far. So, distributions. Okay. What do you mean by a distribution? When I say I have a distribution of scores, what am I referring to? What does the word distribution mean? Scores or a distribution of data basically tells you how the data is distributed, how it's spread. So it also tells you, for example, what is the frequency of a particular score. So if you say how many people got a 90 in the exam, the distribution will give you that information. If you say what percentile is 55 exam score, that means what percentage of people got 55 or less, the distribution will give you that. Okay? So the moment you hear the word distribution, all you're saying is how is the data spread out and what values does it contain. Okay? That's really what we're getting at. Remember the histogram that we drew? The histogram is a representation of the distribution of data. We are now going to look at a very specific distribution called the normal distribution. And you already know what the normal distribution is. Many of you know it as the bell-shaped curve. Okay, the normal distribution is nothing but the bell-shaped curve that you come across many times in life. Okay, so we're going to talk about a specific type of distribution, but I just want you to remember the basic definition of a distribution, which is basically how is the data spread. Okay. So here is an example of a distribution. Look at the distribution on the left-hand side. Okay. And would you agree that this part here looks like a histogram? Right? What does a histogram say? On the x-axis, it gives you values. The y-axis gives you how many are there of those values. That's what a histogram does. Okay? So the bar basically is a histogram. What is the smooth curve on it? The smooth curve says, yeah, I have only collected information on a subset of people. The smooth curve basically says, here is really the actual representation of how it should look from the population. Okay? So the smooth curve is essentially smoothing out the jagged points that the histogram is showing. But now it's very easy. What proportion of scores are between this point and this point? Would you agree 100% of all scores? Right? Because those are the two endpoints. So if I do a smooth curve on it, the proportion of scores that fall under the smooth curve will always equal, therefore. Okay, let me rephrase this. All the scores fall under the smooth curve, right? So that means nobody else is going to get a grade which is not under the smooth curve. So 100% of the students get a value somewhere in the smooth curve. Therefore, the area under the smooth curve will always equal 100%, or in our case, 1. Okay, why is that important? Because now it becomes easy. So if we ask, let's take this point right here, and let's say that answer is 7. I can ask the question, what percentage of people got a score less than or equal to 7? You would say, the percentage of people who got a score less than or equal to 7 is nothing but this area under the smooth curve. Okay? The total area under the smooth curve is always 1. Therefore, the area under the smooth curve to the left of 7, in this case it looks like exactly half, would be 50%. So what would that number 7 represent if its area was exactly 50%? I'm saying a grade equivalent vocabulary score of 7 lies right in the middle. 50% of students got a score of 7 or less. So what is that number 7? We know it. Median. See? Now I can ask you, can you identify for me approximately the 75th percentile? You would say, find me a number such that the area to the left would be equal to 75%. Would you agree it would be somewhere here? So that this area is 75%? Does that make sense? That's it. So the 75th percentile would be the number 9. Because I know that the total area under the curve is 1, any proportion automatically indicates that percentile. Okay? So two key facts. One, the shape indicates how the data is spread out. If I asked you which value occurs the most frequently, you would say, which appears the most frequently? 7. And that is called the mode. Mode is the value that appears the most frequently in a data set. So in this case, this value 7 is the mode. Okay. Now, because of the way the curve is, 7 also happens to be the median, because it splits the data exactly in half. Okay, it's not always true, but for a normal distribution, it's going to be true. Okay. So what we're going to do is take a look at a distribution that looks like this bell-shaped curve, and look at some of the properties. So remember the table that I handed out. If you look at the table straight away, you'll see that it's exactly bell-shaped. Okay? And we're going to use the table to actually calculate areas. But just to show you why we need a table and why can't we do it elsewhere. So if this is represented by a function, can you recollect how one would calculate the area under a curve? Anybody remember their calculus? How do you calculate the area under a curve? All that, sorry? Take what? You integrate it with respect to the two values, and that is how you calculate the area under a curve. Now, we could actually do the integration for each time we have the problem, but fortunately for us, life is a little simpler, and that's why we have a table. Okay? So we're going to use the table which has actually done all the integration for you and put the values. And once we get used to using the table, we'll go to jump software, which makes it even easier. Okay, but first we're going to start with the table. So. See, I did tell something not to ring. No? Okay, so we can have density or distribution curves which look very different. All of them are valid. The only thing that unites all of them is that the total area under the curve will always equal 1. Always. So the only thing you need to know is that the area under the curve always equal to 1. Okay, that's very important. So this is called a uniform distribution. Okay, we won't worry about that. But tell me, take a look at this. Is that symmetrical or skewed? Left or right skewed? Right skewed. Very good. So if it's right skewed, the mean will be dashed to the median. To the right of the median. Very good. And therefore, this is an example of left skewed. Very good. And what is this? Maybe it's an elephant. No, sorry. I don't know what the heck that is. Okay, normal distribution. So remember the word distribution? It's telling you how the data is spread out. It's also going to tell you at each value how many data points, how many people have the same score. Okay. First of all, the normal distribution is a family of symmetrical shaped curves. So it's completely symmetrical. What does that mean? If I were to draw a line in the middle right here, it divides the curve exactly into two equal parts. Therefore, you see the line right there. Would you say that that line is also the mode? Would you say that is also the median? Aha! Now, that line the data point there is also the mean. So here is the first property. In a normal distribution, the mean, median, and mode are all the same point. Make sense? The mean of a distribution, in this case a normal distribution, is given by this Greek character mu. The Greek letter mu indicates the mean of the distribution or the mean of the population. The standard deviation of the distribution is given by the letter sigma, right here. So here is how I'm going to write it. If something follows a normal distribution, suppose I say test scores follow a normal distribution. Let's say I represent test scores by the letter X. I'm going to say test scores is distributed as, that squiggle means distributed as, a normal distribution, that's the letter N, with the mean mu and with the standard deviation sigma. That's notation, okay? We are going to use that notation a lot. So let's just take an example to illustrate it before I come to the properties again. So if I say that X and let's say X represents the test scores. Can you read that thing for me on the right hand side? What does that mean? X distributed as what type of distribution? Normal. What's the mean of the distribution? 55. And what's the standard deviation? 5. Okay, so we know that part. The mean of the distribution means what? The average test score for that class was 55. We also know that for a normal distribution, the mean is the same as the median. So, what percentile is the score 55? What percentile is the score 55? If you got a 55 in the class, what percentile are you? You are at 50. Exactly. Which score did the students get the most? 55. That's the mode. Okay? So it turns out that 55 is not only the mean, it's also the median and the score that happens the most in the class. Okay? And 5 is the standard deviation. Now let's take a look at the shape of the distribution. Do we like a big standard deviation or do we like a small standard deviation? Given a choice, we want small, right? So what happens when the standard deviation increases? What happens to the data? It gets spread out. Agreed? So take a look at these two curves. This is one, and this, I'll call this A, I'll call this B. Which one do you think has greater standard deviation? Which one do you, A? What do you guys say A? It does. Isn't the data spread out a lot more? See? So here's the beauty of it. The more it's spread out, larger the standard deviation. Okay? So standard deviation affects the spread of data. The mean affects where it is located. Okay? Now, the curve itself, which we called as f of x, this is the formula for it. Okay? 1 by sigma, 1 by square root of 2 pi e power minus x minus the mean by standard deviation whole square. Now, here's the problem. Anytime you want to calculate the area under the curve, so if you were to say, can you tell me what is the area between, say, a value A and a value B, I would have to take this function and integrate it between A to B f of x dx. Okay? And to be honest, with a normal distribution, it's a big pain. For certain curves, we can calculate it very easily, but for a normal distribution, it's a big pain. So that's why that having the table is very useful for us, and I'll come to that. But I want to ask you, what do you think is this area equal to? this area, total, from here to here. 0.5. Agreed? So we know that the total area is equal to 1. Agreed? So all I have to do is to say, look, I know a student who got a score of 62. I want to know what percentile is that score. To calculate that, you would say, oh, all I have to do is find this whole area. I think my connection is having a nervous breakdown. It's seeing different colors. So, okay, all you have to do is find that area. Okay, so the whole process today is to see how to get at that area. Once we do that, then I can say tomorrow your exam scores are normally distributed with that mean and that standard deviation. Find me the score at the 80th percentile. You should have no problem. Okay, so let's continue on this. So in this particular top diagram, you can see that all three of them have the same mean. Well, that's 15. And by the way, that's a straight line. If it looks wavy, that means you guys had too much too, you know what. So, if that's 15, which one has the greatest spread? Basically, you already answered this question, just to reinforce it. Which color has the greatest spread? The red one, right? By the way, what are three primary colors? Blue, red, yellow is not a primary color. That's what they teach you in primary school, and that's all wrong. Red, green, and blue. What are the three subtractive primary colors? Anybody have an inkjet printer? Cyan, magenta? No, yellow. CMYK. So just to correct your bad primary school education, when it comes to primary identity colors, it's red, green, and blue. They do yellow because many times you can duplicate everything else with yellow. And that's why they don't teach you. But if you ever look at a monitor, oh, you guys haven't looked at a monitor, you all look at LCDs now. But you know, when I was young, we used to have the CRTs. You know, the categorical tubes with RGB tubes, but that's what the primary colors are. Now you might wonder what that has to do with statistics. Absolutely nothing. So in this particular case, the means are different, but would you agree that the standard deviations are the same in the second case? Because the distribution of curves look identical except shifted. Okay? So when the standard deviation is the same, the spread of data will be identical, but if the location, which is the mean, is different, then obviously the curve moves wherever the location is. Okay? That's basically it. Okay, so we're going to start calculating areas. We're going to start calculating areas by using first thing called a rule of thumb for normal distributions. If somebody tells you we have a normal distribution, then we know the following things. We know that in this particular example, the mean is 64.5 and the standard deviation is 2.5. Okay. So if I take a score, let's assume in this case the height, the average height of people in my sample is 64.5. So if I consider everybody who's one standard deviation above or below that average. So one standard deviation above would be 64.5 plus 2.5 or 67 inches. Okay? And one standard deviation below would be 64.5 minus 2.5, 62 inches. If somebody says, what proportion of people in your sample are between 62 and 67, and if they tell me that this is like a normal distribution, I don't even have to do anything. I'll say approximately 68%. Okay. This is very interesting because tomorrow, if your instructor comes back and says, oh, exam scores were normally distributed with a mean of 80 and a standard deviation of 10, then you know that 68% of students had a score between 70 and 90. See, I didn't even have to take a look at the scores. I could tell you that 68% of you had a score between 1 standard deviation below the mean and 1 standard deviation above the mean. Okay? Interesting? We can do it for 2 standard deviations. If I go 2 standard deviations below to 2 standard deviations above, the answer becomes 95%. For 3 standard deviations, 99.7%. Now, do you ever remember that, I don't know if you ever, sometimes people make a statement saying, oh, you know, his average is more than 3 standard deviations above. What does it mean? What percentage of people are more than 3 standard deviations away from the mean, if it is normal? What percentage of people have a score more than 3 standard deviations beyond the mean, either positive or negative? 3/10 or 0.3% of the people, right? A really small amount, very rare. That's why if you got a score which is more than 3 standard deviations from the mean, we hope it's in the positive direction, right? Like a salary, right? You want 3 standard deviations above the mean, for example. Or a score, 3 standard deviations above the average score. Okay? In a normal distribution, that only 0.3% of the people have that score. So now I can ask you, if I got a score of 67, think carefully before you answer this. At what percentile is that score? If you got a score of 67, at what percentile is that score? I said think carefully, right? Come on, you can do it. Just requires one more step of calculation. You can discuss among yourselves if you want to give me an answer on that. How much? Yeah? Are you guys pulling numbers out of a hat? Except I don't see you guys wearing a hat. How did you get 95? No. It's all there. You just have to put it together.
84.
84. That's right. How did you do it?
I saw 64.5 was half.
Okay, hold on.
That's in 68.
Again, that's a straight line.
Then I took the other half of 68 and added
What? Say it again.
I added half of 68, which is 34 to 52.
So, from here to here is how much? 34. Everybody agree that's 34? Everybody see that? Everybody see that that is 34. Okay, once you see that, then it's straightforward. Why? What is this area? 50%. Agreed? Therefore, the answer is 84th percentile. Make sense? From here to here is 68. Then we have a light show, but 60. Right? Make sense? Okay.
I have a question.
Yes.
Your original question was what percent?
What percentile?
267.
Is 67. The number 67. This 67.
And you'd always go from left to right?
Well, percentile is always the area to the left of the number. Okay? So, all I'm asking is, what is the area to the left of 67? And it turns out in this case to be 84%. Okay? Okay, just to argument's sake, what is the percentile for 72? That's right. 72 would be at 99.85 percentile. Do you guys see it? No? What happened? Math doesn't extend to the 90s? The same logic, or let me try a different logic, okay? What is the percentile from this number to this number? 99.7? How much is left? 0.3. Agreed? So would you agree that this area right here would be half of 0.3, which is 0.15, and this area here is 0.15? Agreed? Therefore, the area from here to here would be 99.7 plus the 0.15. I gotta do something about this. I just leave it at yellow instead of flashing lights. I'll try and get it fixed. Okay. Does that make sense? Okay. Okay, so here's the beauty of it. Because we know that all normal distributions look the same way and behave the same way, anytime we have to calculate a value for any normal distribution, we can always convert it to what we call as the standard normal. The standard normal has these unbelievable properties. What is it? The standard normal is given as N01. So can you tell me what they are? What is the 0? 0 is the mean and 1 would be standard deviation. So here is the nice property. The standard normal always has a mean of 0 and a standard deviation of 1. So I can take any normal distribution, convert it to the standard normal. Then all I need is one table to look at the area under the standard normal. This table. So this table that you have is the area under the standard normal. So if you look at it, it will actually look at table A, page T2 on the left. It will say table entry for Z is the area under the standard normal curve. So automatically this normal distribution has a mean of 0 and a standard deviation of 1. So if you want to do it, write it down there. Just put down N01. That way you won't forget what the mean and standard deviation are. Standard normal by definition is N01. Okay? So let's take a look at this conversion. On the left hand side is the normal distribution that we looked at. Again, the normal distribution has a mean of, no, on the left hand side, 64.5 and a standard deviation of 2.5. Now think carefully about this, okay? The number 67 on the left hand side was how many standard deviation above the mean? 1. Everybody agree? Okay. Now take a look at the right hand side. What is the mean? 0. What's the standard deviation? 1. So if I do my conversion correctly, the number 67 should become what number there? That's it. So all we are doing is taking a value here and converting equivalently to a standard normal. So let's do that, okay? Let's see if it works. So let's take the number 67. I want you to apply the following formula. The value on this is, I'm going to call it x. The value here, I'm going to call it z. Okay? And this is what I'm going to do. The z value here is going to be whatever value you choose on this curve minus the mean divided by the standard deviation. Okay? So let's take this. So let's take 67. 67 minus, what is the mean here? 64.5. Agreed? So minus 64.5 divided by, what's the standard deviation? 2.5. Agreed? What do you think this comes out to be? 1. Can you try another conversion? Let's pick another number. How about 70? Can you do it for a value of 70? Can you tell me the corresponding z? Take 70 and convert it. See what happens. This yellow is driving me nuts. I feel I have jaundice. Maybe it's a new strain of the swine flu. It's the yellow swine flu. What did you get? Did you get exactly 2? 2.2. Okay. Are you guys seeing 2.2? So that would become 70 minus 64.5 divided by 2.5. 2.2. So would you agree that 2.2 would be somewhere here? Which makes sense, right? 70 was somewhere here. Make sense? Are you all, first of all, seeing the calculation? Any problem with the calculation? Very important. Because if you get this wrong, you're going to be in real trouble. Okay. The values on this scale are called z-scores. The values on that scale are called z-scores. What is the total area under the curve? 1. Okay? So if I give you a z-score, you look up the value on the x-axis. When you look up the value on the x-axis, you're going to get an area. If I give you an area, you look up the area and you'll get a z-score. Okay? So we're going to do problems with both. But any issue with converting from any normal distribution to a standard normal? Are you okay with the calculation? The calculation is very simple. Take the value, subtract the mean, divide the difference by the standard deviation. That process is called standardization. And that will always be true. The process is always the same. Take the value, subtract the mean from it, divide the difference by the standard deviation. Okay? So, formally, this is how we do it. X minus mu divided by sigma gives you the value on the standard normal for us. So we have seen that. I don't want to go further into that. Okay. Those of you cubes, where do I see them? McKinsey? No, what's the name? Before you click. Okay, so let's take an actual, slightly more difficult problem and calculate a percentile. So it says women's size follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5. What percent of women are shorter than 67? We already did this, didn't we? Okay, let's change the problem. Let's make it, we already did this. 70.5. And let's make it 70.5. So what is the first step? The first step, anytime you're dealing with a normal distribution, is standardize. Always. The moment you get a normal distribution problem, standardize. What are we going to standardize? We're going to standardize this number 70.5. Okay. So if I take the value 70.5, can you tell me what the corresponding z value is? 70.5 minus 64.5 divided by, okay, which is 2.4. So the problem translates to what? Asking the question, what percentage of women are shorter than 70.5 inches is the same as asking standard normal, 0, 2.4, that's right. What is this area equal to? Would you agree that these two problems are the same now? They are equivalent problems? Right? All I've done is taken the 70.5 and translated in 2.4. So if I want to do a line, this point becomes this point. The mean becomes that. Make sense? Now, this is called as what score? Z-score. Okay, let's use the table now. Look at table T2. Look at what's shaded on the top. The shaded part is what's given inside the table. So would you agree that the shaded part is the area? Agreed? And the total area under the curve is equal to 1. Therefore, what's inside will never exceed 1. Now, what the x-axis gives you what? The z-score. So this problem, would you agree, is that we have a z-score and we need to find an area? So what we need to do is first look for the number 2.4. And where do I find the z-score? Look at the first column in the table. Do you see the number 2.4? You will not see it in you will not see it in table T2, but turn it around. Actually, if I turn it around, I can't see it and you can. Let me turn it around this way. You will see it in T3. Look for the number 2.4. Do you see it? Now, would you agree that 2.4 is the same as 2.400? So, look at the second column. On the top row, it says 0.00. Look for the intersection of the row 2.4 and the column 0.00. What do you see? Therefore, the answer is 99.18% of women are shorter than 70.5 inches. Doesn't it beat doing integration? Okay. So let's do more problems. Okay, this is what I was showing you, and I'll come back to this table. But let's see if I can. Here's a problem you can do for both. Okay. So here is a effect of vitamins and better food on gestation. Okay, in malnourished mothers. Okay. So the goal is to obtain pregnancies which are 240 days or longer. So we have two things. So let's take a look at the two things. The blue curve has a mean of what? And a standard deviation. And the orange curve has a mean of 266 and a standard deviation of 15. Right? So would you agree that just by looking at it, you know that on average, the women who are taking vitamins and better food have a longer gestation period on average. Does it make sense? That the mean has already shifted by 16 days. Right? Not only that, look at the standard deviation. The standard deviation is smaller. That means in the other case where they just had vitamins, it spread out a lot more. There were people obviously who did pretty well. In fact, there are people in the blue line who had 300 days. But in the orange line, because the standard deviation is smaller, they still had people more than 300 days. Okay, so what we want to find out is what percentage of women had more than 240 days pregnancy in either of the two. So which one shall we start with? The vitamins? Okay, so let's take a look at the blue curve. So 240 would be right here. What we want to calculate is this. Okay, what's step number 1 in dealing with a normal distribution? Standardize. So can we standardize? So let's start with X is normal with mean 250 and standard deviation 20. Can we standardize the number 240? That would be 240 minus 250 divided by 20. This is how much? Negative 0.5. What is negative 0.5? What do we call that? A z-score. Very good. Can we go back to the table? Can you find negative 0.5? You find it? Okay, what's the area corresponding to negative 0.5? Do you see that as 0.3085? But look at the top of the table. 3085 is what? The area to the left or the area to the right? To the left. So we know that this is 3085. So what is the area to the right? $6915. Are you guys seeing this? Don't copy it. I want you to understand it, please. Make sure you know where the 6915 is coming from. The total area under the curve is 1. The table gives you the area to the left, which is 0.3085. Therefore, the area to the right is 1 minus 3085, which is 6915. So what percentage of the what percentage of women have a gestation period more than 240 days when they are only on vitamins? 69.15. Or in other words, what percentile score is 240? 30.85. Very good. Because percentile by definition is the area to the left. Can you do the same calculation for the one with vitamins and better food? What we want to do is calculate, therefore, this area. Agreed? So let's standardize. We know that X is normal 266 and 15. So Z is 240 minus 266 by 15. 26 by 15, which is what? (1.733). Negative 1.733. And now it becomes interesting. Can you identify negative 1.733 in this table? Okay, let's start with negative 1.7. Can you find negative 1.7? Okay, now on the top, look for 0.03. So what do you see? Right, 0.0418. So this area here is 0.0418. Therefore, this area here is 9582. Are you seeing this? Because I'm looking for the number negative 1.733. Okay? What the top part gives you is the second decimal point. Okay? Look at the difference. Yes, sir. Oh, yeah. I don't know if I have. I don't have the exact negative 1.7. Do you have anybody who got a table? Can you show it to him, please? Yes, sir.
It was like 1.735.
1.735. You would take the average between 1.73 and 1.74. Okay? But it really, I mean, that level of approximation, it really won't vary too much. Okay? So, we went from 69.15% to 95.82%. Big difference. Okay? So we are using everything by converting it to the standard normal, then looking up the table corresponding to it. Okay? Do you still have a question? You're getting a question answered? Okay, because the top row gives you the second decimal point. We have 1.73, right? So if you look at the row 1.7, okay. Okay, we actually calculated all this. So. Okay, so we can use the table backward now. What does it mean? Not that we're going to stand on our head or something like that. We're going to look at the area and tell you the z-score. Now tell me again what the z-scores represent. If you get a z-score of -3, what is it telling you? If you get your exam score, do you want a positive z-score or you want a negative z-score? Okay, so would you want +3 or -3? What does +3 indicate then? Very good. That means your score is 3 standard deviations above the mean. And what percentage of people get a score above you? If you had a 3 standard deviations above the mean score. Not 3/10, half of that. 0.15% of the people had a score more than you. Okay? So you can see that the z-scores are really how many standard deviations above or below the mean we are. Okay? So if I give you an area, we want to find out the corresponding z-score. So think carefully. If I give you an area less than, let's say I'm calculating the area to the left, okay? And I give you a 45 percentile. Will your z-score be negative, 0 or positive? You are at the 45th percentile. Will your z-score be negative, 0 or positive? Negative. If I gave you a percentile of 50, your z-score is? Very good. Any percentile more than 50, automatically positive z-score. This is area to the left. Let's just make sure your brain doesn't get scrambled too much. The area to the right is 45%. Will your z-score be negative, 0 or positive? Are you positive? Okay. The area to the right is 45% of your score. Will your z-score be negative, 0 or positive? Are you sure? It will be positive. If the area to the right is 45%, What percentile is your score? 55th percentile. Agreed? Okay, so that's basically the calculation. So let's take a problem and we can come back and calculate it. So, how long are the longest 75% of pregnancies when mothers with malnutrition are given vitamins and better food? So that's the question we want. So that means we want the area to the right to be 75%. Agreed? So let's call this number x. Okay, we don't know what the value of x is. Or they actually calculated for you, which I didn't want you to do it. Okay, but let's say that's x. Why don't we change the problem? 72%. That way you can't just use the answer that's given there. Okay, let's say 72%. We want to know x. Would you agree, first of all, x will be below the mean? Because what percentile is x at? 28th percentile. Right? The area to the left is 28%. Would you agree that this is 28%? Okay, so we know that z score for x is going to be negative. What is step number 1 in dealing with a normal distribution? Standardize. Just blindly just standardize. So let's take this number and standardize it. We get z is x minus the mean 266 divided by standard deviation of 15. Agreed? Now, do we know what the z value is? Can you look this up? You're going to look for what number? 28%, which would be 0.2800, right? But where are you going to look? Are you going to look at the z value or are you going to look inside? You're going to look inside. Why are you looking at 28% and not 72%? Why are you looking at 28% and not 72%? You don't like 72? It is bad to you? So what? Is there a practical reason why you want to look at 28 and not 72? Sorry? I'm sorry, I didn't hear you. Practical reason. Why? No? That's right. The table. The table only gives you areas to the left. If you had a table that gives you area to the right, practical reason is the table gives you areas to the left. That's why we have to convert it to 28%. When we do the software, we don't have that problem. It will give you both areas. Okay? Because the table only gives you areas to the left, we have to look at. So can you identify 28? That's pretty close. Do you see 0.2810? And so the answer would be negative 0.58. You see negative 0.58? Okay. So we know that this value here is negative 0.58. First of all of you saying negative 0.58? No? Look for the value 0.28 inside the table. Look for 0.28 inside. The closest you will see is 0.2810. Okay? So that's negative 0.58. Can you tell me the value of x? What is the value of x? Oh, before you even calculate it, can I ask you the following? How many standard deviations is the value of x from the mean? How many standard deviations is the value of x from the mean? What? What is z-score? 0.58. What does z-score represent? The number of standard deviations below the mean. So what should x be? How many standard deviations should it be? 0.58. X is 0.58 standard deviations below the mean. That's what z-score represents. Okay. So can you calculate x? So would you agree that x is 266 plus negative 0.58 times 15? How much? 2? You get a smaller value than 266.
I got 237.3.
237 point?
257.
257 point? You can't be 250. You guys are all messing me up. 240.137. What? 250. What is the answer? Next time I want to set up a multiple choice exam, I'm asking the class for the answers. Give me a multiple choice. 257.3. Okay? Okay. So here's what we're going to do. The moment you come on Tuesday, I'm going to test you. So you're going to have your clickers ready for all this. So,